So I don't want to cut your lunch, so let's go to the next session. The next session, I will pass to site investigation. And we have two speakers. First speaker is Professor Robert Liang from University of Dayton. Yeah, and yeah, great to see you back, Robert.
Yeah, thanks. Yes, good morning. First of all, I know this is between now and your lunchtime, so I'll make my presentation relatively short. But first of all, I want to acknowledge my thanks to Kenichi and all the organizing members from UC Berkeley's Geosystem group that kindly invite me to give a talk. So I would relay my story to you in terms of my work on the using of the data science in characterizing the geological models using a very limited number of investigation data. So, so first of all, I guess this is the picture that my last met with Professor Mitchell. It was back in 2019. At that time, Professor Mitchell was in Columbus, Ohio, giving a distinguished T.H. Wu lecture. And it was very fortunate that he has time to meet with me privately to catch up with my research work at that time. So it was afternoon lunch organized by the Ohio State faculty members, and prior to his lecture, that's about 3 hours gap. So he and I have a very, very long conversation. So at that time, I was telling him that I started working on the use of some of the artificial intelligence data science principles together with stochastic simulations, try to establish stratigraphic models using the in-situ testing data such as cone penetration data, while at the same time we can quantify the uncertainties of the inferences based on those limited data. So Professor Mitchell was at first very suspicious, okay? He said, it's a very challenging problem, and even you can do it, can the profession trust you? Because it's related to a lot of numerical simulations and data clustering, statistical analysis. And also he outlined a lot of challenges at that time. So I'm going to summarize some of his points that provides the guidance while I'm embarking on research in this direction. But first of all, I think I would be remiss not to talk about the impact that Professor Mitchell had on me during my early stages as a graduate student. As you know, I came from foreign country. I came from Taiwan in 1980s. I got my master's degree at NC State University under Harvey Walls. And I said, Harvey told me, you can stay here and do PhD with me. And told him, thank you, but I really like to go to Berkeley because I study all the works and all the famous people are in Berkeley. So Professor Walls was very, very kind to introduce me to Berkeley, and I was very lucky to get admitted. I know Professor Duncan at that time was the graduate committee admission, I guess, director. So I was very lucky in 1981, I came to Berkeley. And, I was relatively new in this country, so I didn't know a lot of stuff. But I was very lucky at that time, thanks to Professor Ed. He just, together with Jim, wrote a very big NSA proposal, and they got that big proposal. It's a continuation of the work started with Rudy on the constitutive modeling of soft clay, considering consolidation and creep, and then Ed continue on with the expanded modeling, and then they wrote a proposal. The idea is to use the centrifuge to validate the constitutive model. So at that time, I was very lucky. Professor Mitchell accepted me as his graduate student, and I was able to be part of his family from that point on. But anyway, some of the things, looking back the first year with Professor Mitchell, it's not much of the words or the discussions about the technical things, but rather those things I listed here really embedded in my mind and has a great influences on me that now I reflect back, it's more so than anything else. So I can remember vividly the first semester I was here, Professor Mitchell invited all the graduate students to his house for Christmas break. And I remember that time, Tom Brandon was there, I think Scott was there, plus other contemporary graduate students there. And Professor Mitchell did a game. I don't know the meaning of that. It's just very simple, doing things, and at the end, he's asking people, can you observe anything that's noteworthy? So I learned from that exercise, his point of doing that game for all his graduate students is really embedding us that as a geotechnical engineer, you need to have a sharp eyes and to be very observant. And so that's the number one that I have that in my mind all the time. It just, get your eyes wide open when you go to the field, when you observe things, try to see anything unusual. So that's one thing that it kind of stayed with me all the time. Well, the other thing, of course, is when we start doing the centrifuge testing, and it was the first one in the United States, and we are going to take the big centrifuge from the Ames Research Center and to the UC Davis campus. And so, in the United States, other than UC Davis is a small centrifuge, there's still a lot of gaps in terms of knowledge of how we can do the experiments using the centrifuge at that time. That was between early 1980s. And one time in the afternoon, Professor Mitchell asked me, Robert, let's go out and look at all the camera systems. And it was really a very nice ride with him because I was kind of, the very naive graduate students. And I remember Professor Mitchell had a Honda Accord at the time, and he drove me along the way to Oakland and visit some of the camera shops. And the way he talked to the salesperson, the experts over there, the way he has so much inquisitive questions about it is really eye-opening for me. So from there, I learned my lesson number 2. Not so much from his teaching to me directly, just by being with him, observing him, how he tried to get all the information he needs, being able to make the informed decision. That's kind of very, very important lesson for me. And certainly the last thing I want to say is that also Professor Mitchell afforded me the opportunity to work on multiple projects. And one of the projects I remember vividly, I think that's either Scott's Huntsman's project or Phil Tringotti's project in time. But I was involved in terms of running the triaxial test at the Richmond field station with the microphone embedded there and try to pick up all the microphone sounds. And the reason we do that is, according to Professor Mitchell, is that he has a hypothesis. The shearing mechanisms of sand comes from rolling, crushing, and many other slidings. And his hypothesis is that all this motion during shearing is going to produce different sound frequencies. So he wants to prove that. So I was the one, together with other, my contemporary graduate students, but my job is to just look at a triaxial test and run the test and be able to discern and to prove whether the hypothesis will work or not. So from there, I think I learned a lot. When you do your research, scientifically, you have a hypothesis and figure out a way to prove or disapprove your hypothesis. So I just list those little things that happened in my first year as a graduate student at Berkeley under Professor Mitchell. I always call him Professor Mitchell because to me, he's just a giant. And I have so much respect for him. I consider myself extremely lucky to be able to accept it as his graduate student and be in the very, very prestigious institution together with many contemporary friends over there. I know Steve Kramer, Tom Brandon, just to name a few. But anyway, so I guess the conversation about my thinking at that time is, can we use AI techniques and to kind of develop geological stratification models? And the way he told me is that, so anyway, so this is summarize what I just said, so not just the words or instructions, but his deeds that actually influenced me more so than anything else. But anyway, so I just want to be brief. At that time, he pointed out, this is my vision there. He said, traditionally, we kind of interpret the site, stratigraphic conditions more or less deterministic based on the engineering judgment, based on the best understanding of the geological processes at the site. What can we migrate to the digital transformation in the sense that we can use machine learning, we can use stochastic simulations, and we can construct, stratigraphic models, yet we can have a quantified numbers to ascertain what's the comfort level we have or the uncertainty level that we have. So that's kind of motivation to get involved with this. And of course, Professor Mitchell will talk about, a lot of his concerns, and in a sense, it's giving me the direction. If you want to do this, you need to think about those things. So for example, uncertainty, certainly if we are doing the data science, looking at the data, uncertainties need to be quantified through the root from the data, the authenticity of the data. And of course, the base and machine learning is really different from the frequentist interpretation. And then certainly the investigation data at a particular site is going to be always finite because we have to recognize and respect location-specific geological models. So we can't really readily transfer what you learn from one side and transfer that to the other side because the locality and uniqueness of the site is going to be always there. So among some of the challenges that Professor Mitchell mentioned about, for example, multivariate nature of the data, uncertainty and fidelity of the data, sparse and incompleteness and potentially corrupted, and 3D spatial variations. Those are the nature of the data I want to use to build my machine learning model. So that's the first thing, as a big picture thing that Professor Mitchell was able to, articulate that during our conversation. And certainly we all understand, we have to recognize the specificity of the site condition. One side is not unique, it's different from the other side. And finally, of course, want to make this to be, like a pipeline for feeding into the subsequent reliability-based design, if that, want to have some, practical consequences. So since we have started working in 2017 or 16, and I reported to Jim in 2019, and then after that, we published quite a few. This is just some of the ones. But so if you want to see the details, you're welcome to look at those references. And we also published the article in the Geostrata. That was the magazine, has a special issue on the site investigation. And as you know, we have a standard called DIGS, D-I-G-G-S. And so naturally, I just said when DIGS meets AI, what would be the consequence? What would be the birth of that? So there was an article that related to what we have done. So taking the CPT data as the example, so what we're looking at is, can we do AI to discern the patterns and also to look at the spatial correlations as well as the statistical clustering patterns? So our approach very generally is to utilize, so we have basically have two spaces. One is called physical spaces. That's, if we look at the 1D cone penetration data, we have so-called soil type. So in our stratification, we have to define whether it's clay, sand, or whatnot. And that's we call soil type. It's a hidden layer. And then we have another layer, which is actually observed data, which is actually, if you look at it for cone, is a cone resistance and the friction ratio, right? So, so what we do is, of course, using the Gaussian, we do the actually combine the data into the map the data into the feature space, which is over there is a traditional Robinson chart, and you can do the clustering analysis, and of course the features of the soil types can be analyzed, and the centroid of that cluster represent the mean of that similar soil types, and the shape actually controlled by the covariance matrix. So the idea is that we can run the machine learning together with the stochastic simulations, and then we can get a better discernment of the pattern. And so one of the underlying principles is the energy principle. So we're saying that in natural processes, if you look at point X over there, your neighbors, the one above you, the one below you in your pixel, they tend to be having the same properties, right? So if they are not, and we just give them a jump of the energy. So we calculate the local potential energies based on the simulation result. And of course, the nature wants to stay at the lowest energy level. So from there, we can develop what we call local conditional probabilities. And then we do Bayesian learning as combined with the stochastic simulations. We can train and optimize the parameters, right? So that's kind of the underlying principle is just doing that based on the energy. So this is some of the examples, right? So this is one of the data sets, and we can see that interpretation in terms of the soil index, that's the soil type, and information entropy actually is the major device to quantify the uncertainty. So the higher the value, the entropy value, meaning that the particular soil level or that type of soil classification has higher uncertainty, and so on and so forth. So this is unsupervised machine learning. You don't really have to give them the power training. They will just take the input data and be able to interpret it and provide you with the analysis result. And we can also take the multiple sounding data together and do the analysis for each volume log. So this is, in this case, then we have not only the neighborhood system in the vertical direction, we also have a neighborhood system, you see those reds, in the horizontal directions. So it becomes more complicated, but the principle is the same. But this is just an example where we took the data from New Zealand, 47 CPT data, and at 240 meter by 240 meter region. And we were able to interpret all this data together. So you can see the data that combined 44 versus you just look at one sounding data per se on the right-hand side. So basically, you can observe with more data that can fuse together to interpret for each sounding, you get more consistent result. So yeah, I will be done. So you can see that basically with these combined interpretations, you get more consistency in your interpretation in the vertical direction as well as in the horizontal directions. So that's, again, it's the unsupervised machine learning that together with the stochastic simulations, we were able to do that. Of course, the algorithms were published as a public domain in the GitHub, and there are plenty of users worldwide now already getting into the program and try that for their interpretation of the site conditions. And of course, we expanded into the two-dimensional case. The principle is the same, so I'm not going to dwell into the theories. And then, basically, you ended up with, again, the interpretation is another example. You have multiple soil boiling log data, and using the same algorithms for 2D situations, you will be able to create a stratigraphic information. Underneath, that's the mapping of the uncertainty using the information entrophies. So that will help the engineer to see where they should put additional boreholes to improve the certainty of the interpretation, or that uncertainty can be propagated into your reliability-based design. Okay, again, the same was published in the GitHub. So to summarize, I guess, with detailed discussion with Professor Mitchell in 2019, we kind of have a very good vision in terms of what other challenges are, what was the ultimate outcome that we need to achieve for the profession to adopt it. But I think, and this is currently what we have is using the AI technology together with stochastic simulations to be able to interpret CPT data for creating the stratigraphic models with the uncertainty quantifier. So at the end, I'm saying, I guess a lot of my fellow graduate students will feel the same. We thank Professor Mitchell for his guidance, inspiration, and learning mentorships throughout my early careers as a graduate student and into my, entire career. And so we will miss him deeply, and certainly will cherish all the memories that we share with him. So with that, thank you very much for your attention.
Our next speaker and the final speaker this morning is Professor Rodrigo Salgado from Purdue University. So, Rodrigo.
Well, good morning. So what I'm going to do is basically go over Professor Mitchell's contributions in CPT, computation testing research, and talk a little bit about, to use Rick's words, my tangential contact with him. So the first time I was aware of Jim was when I walked into a library in Brazil. I had just transferred from chemical engineering to civil engineering. And I walked into the library and I was going through the books that were available, and I ran into fundamentals of soil behavior, and I immediately related to it, seeing all the chemical formulas and so on in there. So that was kind of the first time. Then later on, I got more and more into geotechnical engineering and went to work for a geotechnical specialty contractor. And they had a CPT rig. And that's the second time I kind of came into contact with some of Jim's work. He was, as somebody said, he was early in doing research in topics that were just getting hot, let's say. And the CPT was such a case. So at that time, I ran into Dorganoglu and Mitchell, for example, right? One of the first papers on CPT test interpretation. Then I came to the US for graduate work. I spent a year with Tony Sada, Case Western Reserve. And then I came to Berkeley. I remember to this day that when I visited before I came, trying to decide where to go, my friend Salah was the one who gave me the tour. And I always tell Salah, I think that had something to do with my coming here, in addition to Jim as well. All right, so sometime after I came, Jim and Mike Amielkowski decided to collaborate on research. Mike had been supervising or really doing with his team a lot of calibration chamber testing in Italy. They had literally hundreds of tests by that time already. And I think the interest was how to make sense of all that data. And that's how basically ended up doing a thesis on cone penetration resistance analysis. I am fortunate that I had such a good mentor, such a good PhD advisor, and that I stayed not close to him, but we did cross paths a number of times, and he was very supportive during my career. So here I am with Jim and Mike, who was not officially a co-chair of my thesis, but functionally, pretty much. So I am quite happy in the photo, and either they are happy or they were being very nice to me. But so we had a number of opportunities to meet. This is a photo from Foz do Iguaçu in Brazil. I think Jorge shared this with the Jim Mitchell website. And there is Jim and Bunny. Jim came to Purdue a number of times. In 2006, he gave the Lovell lecture at Purdue. And so here he is. This is probably after the lecture when we had a kind of a discussion about a number of things. And so Monica is looking on probably an answer to a student's question or something like that. And during the same event, he signed a number of copies of the book to students and also my own copy. I guess after July 2025, I'll need to concoct an event in which Kenichi and Catherine are together, and we'll get new autographs. And so this is GeoCongress. I think a student ended up taking this photo and shared it with me. It's Roman, myself, and Jim talking about most certainly CPT. In 2015, Holly and Jim came to visit. He gave always a lecture. He was always very serious about giving the lecture, but we had some good times together. And I owe to this visit the knowledge about one of the best TV series that has ever been made, and that's thanks to Holly. We made mutual promises of a repeat, but it never happened. So I think I read somewhere that you are the average of the 6 people closest to you. And having spent a little bit of time with both Bunny and Holly, I can see some of that truth in there. I can see how not only Jim was a wise and kind person that we've all been saying, but how those closest to him must have an impact as well. Now on to his contributions to CPT research. We can think of his contributions, or anyone's contributions, I think, more or less as falling in three boxes, right? One would be the development of devices. So putting sensors in a cone penetrometer, for example, or coming up with a new device. And then kind of exploring things about a soil profile that you really can only do with the CPT, right? And finally, interpretation of the CPT. And that's kind of what I worked on with him. But I want to go over each of those and give a few examples. This is by no means an exhaustive list of papers. But in terms of device development, there were two devices that I think he was very interested in developing. One was the acoustic cone penetrometer, and the other was a lateral stress measurement cone penetrometer. So in this paper, for example, by Villet and others, you can see just some of what's in the paper in terms of results. So basically, they explored peak amplitude of noise and frequency, content of the noise, and whether those two things could be related to soil state, to sand state, relative density, and effective stress. There were some interesting observations that were made, such as the sources of noise being either at the contact of the penetrometer with the soil particles, or perhaps from crushing of particles away from the cone. So it was interesting, kind of fundamental research in a way. And then there was the lateral stress cone, about which I don't have a slide. Then a lot of his papers have the CPT in them, in this role that I would say is, what can I do with the CPT? What do I really need to use the CPT for? You know, that would be hard to do with other methods of investigation. So, of course, it would be hard to do an SPT on the moon, but you can come up with a portable cone penetrometer. So he was the PI in this so-called soil mechanics experiment of NASA. And you got little soil profiles from those CPTs, right? Cone resistance versus depth for shallow depths at low confining stress because of the lower gravity. And we reanalyzed that for a conference. To make the story short, it's pretty dense stuff, because you could get measurable cone resistance even though the effective stress was pretty low. The other thing that Jim was interested in was in the causes of the leaning of the Tower of Pisa. How did it start? And if you read this paper from 1977, it's really about what could possibly have started that process. And of course, for something like this, there is nothing like the CPT, because you need enough discretization, right, to detect, for example, whether the problem was layers that, a layer being too thin on one side of the tower, or maybe the layer having the same thickness, but having different stiffness and strength, right? So he went into some of these hypotheses, And the idea then is that it's not sufficient to come up with a general model for your soil profile, but you really want that detail. So Mike Amielkowski and the Tower of Pisa Commission did do a lot of high-quality CPT testing, and you can clearly see that of the hypotheses entertained, really a difference, a pretty significant difference in soil strength and stiffness existed between the two sides, right? The sides from which the tower leaned and the side towards which it leaned. So, the other thing that CPT was useful in highlighting was this potential gain in shear strength or stiffness after deep densification. So the paper, this figure is about deep dynamic compaction, but you could think of blasting as well, deep blasting, anything that could be a source of densification. And the paper has been mentioned earlier today. And clearly, the CPT was something that could show this with a lot more clarity, perhaps, than many other possible in situ tests. By the way, I agree with Chris that this is still kind of a slightly open question. Maybe Catherine and Kenichi will tell us what the real answer is. But Jim's lecture on aging of sand, the continuum enigma, shows that this has continued to be in his mind to the end, because if you try to reproduce, we tried to reproduce some pile setup processes in the lab, for example, and we were not successful. And it's very expensive to do it because you have to wait a long time. Yeah, it's still something to study, I think. All right, last example of use of the CPT. In this paper, Jim and co-authors looked at what happened if you did hydraulic fill by 3 different methods: bottom dropping or dropping from the surface using 2 different methods. And it made a difference. And if you read the paper, it really becomes about soil fabric, right? These different processes lead to a soil with a different fabric, therefore different mechanical response. Now on to interpretation of CPT measurements. As I mentioned before, that's what I worked in. And if you want to reduce it to its essence, you are trying to get certain quantities, I'll call them desired quantities, from measured quantities. What this desired quantities depends on is what you're going to be doing, right? If you are working with some model, you're looking for the parameters in that model. In sand, what we're typically interested in these days is try to determine soil state. So how dense is the sand? What is the effective stress in the soil, and so on and so forth. Because it's impossible to do this from just field testing, because you don't know the quantities you want to get, right? You don't have independent measurements, so then you end up going to the lab for that. And that was the origin of the entire calibration chamber testing model and the calibration chamber testing program in Italy. So this is one of the 2 Italian calibration chambers with which I had a little work, which was involved for a little while anyway. The idea is very simple. You prepare a large sample, you subject it to, at some desired density, you subject it to a known stress state, and you push a cone at the center. All right, then you end up with a lot of data, cone resistance versus soil state, and you want to make sense of that. At the time, in the 1970s, 1980s, the thinking was very much influenced by Liang and Whitman, which this paper, which had a correlation that was basically in terms of vertical effective stress. So standard penetration resistance was a function of vertical effective stress. The initial correlations that were proposed for cone resistance versus soil state were also in terms of vertical effective stress. But there was the realization that maybe over-consolidation and the resulting lateral effective stress would actually have some role to play. But there was no clarity about it. So that's one of the things that we did. If you actually go back and plot, you don't even need to do a theoretical work for it. If you plot cone resistance versus vertical effective stress, mean effective stress, and lateral effective stress, you see a straight line for lateral effective stress, you see some correlation for mean effective stress, and you see no correlation for vertical effective stress. So that work in Italy, also backed up by some work by Guy Holsby and colleagues at Oxford at the time, I think pretty much clarified this point. So cone resistance is a function of lateral effective stress. I might make a comment as to how for example, in this case, the prevailing model or thinking at the time, think of Derganoglu and Mitchell, where you're looking for a bearing capacity failure mechanism. The way we used to think about cone penetration was like a shallow bearing capacity problem, shallow penetration, when you're pushing your foundation in and you need to raise the column of soil next to it. And deep penetration is different. You are actually forcing the thing in by pushing soil laterally aside, right? So that was kind of what went on with that work. We started viewing things in that manner. So now a correlation would have lateral effective stress in it and not vertical effective stress. So you can analyze cone penetration process in many ways. I suppose nowadays I would say material point method is the most effective way. At that time, we used cavity expansion analysis. And the idea is that your cone, when you're pushing it in, is creating a cavity, right? Creating and expanding a cavity. And so the pressure necessary for you to expand the cavity must be correlated to the vertical force that you're using to push it in. So we published this work. I got to still work some more on it for a few more years. I perfected the cavity expansion analysis, Mark Randall, a few years later, and actual penetration resistance analysis of the work with Monica a few years later. All right, the nice thing about having the theoretical capabilities that now you can calculate cone resistance for any combination of values of your input parameters. And you can, if you want to visualize what's going on, you can generate charts like this. They are easy to use in interpretation if you just want a quick check on things. The last paper I'm going to talk about is this work we did with Ross Boulanger. Ross, when I was finishing, he was already at UC Davis, and I think he's in the room. So if I'm saying something wrong, you can. Yeah, I think he was interested in compaction grouting at the time, and basically compaction grouting is in a way a cavity expansion process. So yeah, he wanted a copy of my thesis. In those days, I think I actually had to print it out, right, to share it. So this shows how much time has passed. And later on, instead of compaction grouting, I guess we ended up applying it to liquefaction resistance assessment. So we knew how lateral effective stress affected cone resistance. We knew how it affected the cyclic resistance ratio, so we could come up with CPT-based liquefaction potential curves. and see what effect K0 would have in shifting these curves around. So to conclude, I'm very fortunate that I had Jim as my PhD advisor. I'll just echo a lot of the stuff that has been said here. If I had to summarize it, he was the ultimate reasonable person. And Macron, who is not in the room, will understand this. The reasonable person thinks not only of himself, but all those who are affected by his actions. And I think that is true. Whenever I called him to have a discussion or for advice, I could always count on something. He would have words that were very wise, very reasonable, and very helpful. And I'm very grateful for that. Thank you.